Okay, welcome to our April 2022 Ask a Physicist. Since it is the last Ask a Physicist of this semester, there's not very many announcements. So I will just tell everyone to stay tuned for next semester for our activity that we decide upon for then, something either same thing or similar to what we're doing now. And then lastly, as always, if you have any question, just use the Q&A feature at the bottom of your screen, and we will hopefully get to it at the end. And with that, I will turn it over to the director of the Beyond Center and moderator for the evening, Paul Davies.
Thank you, Jessica, and hello, everybody, and a very warm welcome to regulars and to any newcomers. Please watch this space. We do some really cool stuff in these Ask a Physicist events. Now, I remember a few years ago, we had a visit by Richard Dawkins, the famous biologist, and he gave an after-dinner speech in which he said that he felt strongly that everything can be explained by reductionism, by things that go on at the smallest level, and that some people object and they say, but what about emergence and emergent phenomena? And he said, nobody's ever been able to explain to me what emergence is. Well, I don't know if Richard is logged in, but this evening we are privileged to have Erik Hoel, who will at least try to explain to us the concept of emergence and its good and bad features. So Erik is an interesting individual. He grew up in a bookshop, and indeed he has recently written a novel. It's called The Revelations, which is now out. You want to go and buy it. And in between, he got a PhD with Giulio Tononi on integrated information theory at the University of Wisconsin-Madison. He then had a postdoc at Columbia University, and he's now a research assistant professor at Tufts University. So a very deep thinker about matters of consciousness and matters of emergence and reductionism. And without further ado, I'm going to hand over to him to put us in the picture. And please do feel that you can ask questions, put them, as Jessica has said, into the Q&A channel. So Erik, over to you.
Thank you so much for that introduction, Paul. And it's an absolute pleasure to be here. Can everyone see the slides all right?
Yep.
Perfect. Okay, so what a perfect place to start in terms of, okay, what a perfect place to start in terms of thinking about what would Richard Dawkins think as sort of perhaps our non-resident reductionist. This is, I'm going to be outlining what I think is hopefully a theory of emergence that can appeal to reductionists. That if you're sort of you sort of find it within yourself that you would self-describe as a reductionist, my hope would be that this theory of emergence sort of satisfies you. And at the same time, trying to thread the needle, satisfy people who maybe want something a little bit more. So first is, why is a scientist, and by the way, I'm not a physicist, but why is a scientist discussing emergence? Traditionally, emergence is considered essentially a philosophical subject. There's all sorts of debates around what emergence is or how to classify emergence within the philosophical literature, particularly within analytic philosophy, although even continental philosophy sometimes gets in the mix. And it has some very rigorous, sort of interesting debates. A book I highly recommend is a book called Mind in a Physical World. It says it's about the mind-body problem, but one of the main things it's about is reductionism by Ye-Guang Kim. And this set off a whole host of sort of papers in the classic analytic philosophy tradition. And we can sort of summarize the reductionist position within philosophy as thinking about it like, listen, there's some system, let's call it P1. It has a bunch of micro sort of causes. These might be the physical rules by which atoms sort of relate to one another. And that generates some next time step like P2. And really the idea is that's all you need. Anything else that you sort of describe the system at, like you could describe maybe it as having mental properties or having some other high level properties, you would say those just don't really matter. And really all we need are these micro causes. And this is sort of like a very convincing, I think, reductionist argument. You know, that has some bad consequences, right? Because of course you're made of atoms, right? And so we can sort of say, well, you know, you at sort of a higher level don't really exist. It's just your atoms. And the issue with as many debates in philosophy is that this is never quite resolved, right? The literature just sort of continues going back and forth. So, you know, the way I think about emergence is that occasionally a philosophical concept gets moved into the realm of science or mathematics. And this is actually a good thing, like, but particularly if you're a philosopher, you actually want the domain of philosophy to be slowly sort of getting smaller, right? And so, some historical examples are things like logic, which was originally very much a philosophical issue, and now underlies computer science. You can think of computer science as essentially applied philosophy. Big questions like what is life? Biology has a lot to say about that. Things like infinities, mathematics has a lot to say about that. Psychology was originally basically the provenance of mostly philosophers, and now, of course, is its own academic discipline. Semantics, you can give a good number of these instances of moving a subject into the science or mathematics. And this is sort of what we should hope for with regards to emergence. We want a scientific conception of emergence. But the most important thing to note is that in this scientific conception, it should be relatively boring. And I'll get into what I mean by that. And so what you really want is some sort of idea that shows that it satisfies the basic definitions of emergence, or sort of resolves many of the debates around it, but is somewhat boring simply because it's not magic. And a lot of people who want to talk about emergence essentially at some point want magic. And this is like the big sort of reductionist critique. And really, we should look for something that's relatively boring. And so what I've proposed, along with co-authors, who I'll mention as we go on, is this idea that the boring thing about emergence is that it's really just about noise reduction. Which is sort of a everyday common concept, particularly in information theory. Here we're going to use it in regards to causation, particularly. But I'm going to argue, is a very nice, boring answer, but that satisfies the relevant definition and gives us essentially everything we want out of a notion of emergence. So specifically, causal emergence is noise reduction in causal relationships. So what do I mean by causal relationship? Like, if not X, then not Y, right? These are the sort of things that, for example, Judea Pearl, over at MIT, he's published a really big book called Causation in the early 2000s. His research is all about causal relationships. There's sort of a whole subfield of statistics and mathematics that looks at causal relationships. So science has a pretty, a relatively good grasp at this point about defining and formalizing and talking about causal relationships. And we can piggyback on top of that, because we can just ask, when is there noise reduction in causal relationships? And particularly, I mean noise reduction, I should be clear here, up at a macro scale level of description. So for example, if I have a particular system, I can describe it at a number of different scales, and those scales will contain their own descriptions of causal relationships. And some of these scales, these higher level scales, which I call macro scales, but you could refer to them as dimension reductions or higher level scales, or whatever you want. These macro scales, generally in the relationships between their parts or within their causal relationships, have far less noise than at the micro scale, which is generally very noisy. So to sort of expand this definition a bit, we have to answer a few really fundamental questions. So first of all, what is a causal relationship? I know I gave the example of if not X, then not Y, but we can give some very clear examples of what precisely is a causal relationship. And a causal relationship is, we can think of it as some mathematical relationship between a cause and an effect. So between essentially two things. Those could be elements of a system, they could be states of a system, they could be sort of sort of anything. Generally, its elements are states, states of affairs, or something like that. But sort of, we're going to be talking about all this stuff at a relatively high level. So let's give a brief definition, and don't let this put you off, because I'm going to go through it. So first of all, we can think of causal relationships very broadly, again, as we have sets of causes and sets of effects. And the sets of causes always precede the set of effects, and they have some sort of relationship between them, which is indicated by these arrows here. And you might ask, how do we quantify or formalize a causal relationship mathematically? And it turns out there's a host of answers that people have given to this question. So in other words, there's all sorts of measures of causal relationships. And these measures might, for example, measure the strength of the causal relationship. Sometimes they will refer to it as the power of the causal relationship. Sometimes they'll talk about how informative a cause is for its effect. But they're all quantifications of something like the relationship between the cause and the effect. And all of them are based off of some very simple primitive concepts, things like the amount of noise in the system. If you're in philosophy, you might have heard of sufficiency versus necessity as being fundamental aspects of causation. Those show up in these measures of causation a lot. So here we can think about, let's give a very simple definition of sufficiency. A sufficiency might be, for example, the probability of an effect given a cause, right? Given one of its causes, right? So you might have a highly sufficient effect, which is that the effect always occurs given the cause, or you might have a cause that's, sort of only probabilistically sufficient for its effect, whereas half the time, for example, like in a cancer treatment, maybe half the time the tumor gets smaller, but the other half of the time the treatment doesn't work. And you can define kind of similar basic probabilistic concepts regarding causation, things like necessity, which is essentially the probability of an effect given that its cause did not occur. You can define things like determinism or degeneracy, which are basically complex forms of the sufficiency or necessity. Determinism would be like, how much, if the causes and effects were like a set of state transitions, how much noise will be down in there in the state transitions of the causes and effects. The degeneracy would be like, how many causes lead to the same effect. For example, here we have this effect E, right? Instead of E prime, we've got E over here. And we see that, all the causes lead to E in this case. So this would be a highly degenerate system because many causes lead to the same effect. And there's all sorts of these measures of causation, which are essentially all of them about putting these primitive, what might be called causal primitives, or these basic notions of causation into some relationship. So for example, let's go with eels, as these are names after the names of the discoverers, or you might say proponents of these measures. And some of these measures are decades old, some of them are relatively new. Some are ones that sort of came out of the group that I worked with, which was the effect info. Some of you might recognize many other names on here though. For example, Galton was one of the early statisticians. David Lewis was a very famous philosopher. And we can take some of these examples and just sort of quickly walk through them. So for example, with eels, this would be, you take the sufficiency of the cause plus the necessity of the cause minus 1, and that's your measure of causation for eels, right? And you can see that they all put the sufficiency and necessity in some relationship to one another, right? And so what we found in our research is that these measures of causation generally behave the same. So you can think about it as they're built out of the same components, which are these very simple notions of like probabilistic sufficiency and probabilistic necessity. And because they're built out of the same building blocks, they all end up kind of behaving relatively similar. Sometimes they disagree, but they sort of scale in the same way and are sensitive to the same sort of changes in the systems. So we can think about this as saying that, well, if you look historically at measures of causation, they're all quite similar. In fact, we found that people, in our survey of the literature, we found that people generally will reinvent older things. So for example, the effect information that we thought I wasn't on the first paper of it, but basically my group thought that they sort of invented it. Well, it actually turns out to just be the log of above it, Supes. Judea Pearl discovers like a bunch of these in his books. He kind of proposes all these new definitions of causation, and they're all just these old definitions. So that's good, right? Because it tells us that there's a huge amount of consilience, where generally when smart people think about these measures, about introducing a measure of causation, they basically land on something that sort of behaves very similarly. And that tells us that maybe we can't narrow down causation to a single measure, but we have a family of overlapping measures, a sort of a family resemblance, perhaps like what occurred in complexity in the science of complex systems, where there wasn't really exactly one definition of complexity, but there was sort of an overlapping set of measures of complexity. And similarly, there's an overlapping set of measures of causation. So we can directly measure causation, right? So this is actually something that's very scientifically amenable. So that's a big part of what we're going to need for discussing our theory. The second thing we need is some definition of what is a macro scale, or what is this higher level that we want to be comparing to the lower level, right? And again, we can give pretty easy, simple mathematical definitions of this. Here's from a paper of mine where we're showing off different sorts of macro scales. And I won't go through them all in terms of the details, but you can think of these as, again, these are sort of abstract events or relationships. This could describe a gene regulatory network. It could describe all sorts of different, sort of mechanical systems. This is just the engineering diagram. And you could have something like a micro scale, where here you have A and it goes to B, C, or D, B, C, or D causes E, and so on back and forth. And a macro scale would just be that you could just replace you could just group and coarse grain your system and say, well, listen, B, C, and D all come from the same place. They all go to the same place. They're what's known as equivalence class. And we can just replace them with some higher level description. And the higher level description will actually behave dynamically exactly the same in this instance, right? So here's an example of a very simple system, which we can think of these as state transitions, right? Something like that. This could be like a Markov chain, for example. And here we have, for example, a Markov chain where it has a well-defined microscale and a well-defined macro scale, right? So we can directly compare those. Okay, so then a very simple thing to do, right? Actually, let's go back for a second, is to just say, well, let's just check our measures of causation, which I didn't invent, right? Like this is just the field has been going on. We can just check our measures of causation and see how they behave down at the micro scale, and then check them again up at the macro scale, as if we're sort of making a macro versus micro comparison for, again, the exact same dynamics or the exact same system, right? It's just two different levels of description. And notably, of course, the reductionist should be quite happy here, right? Because we haven't introduced anything new or strange or new laws or anything like that up at the macro scale. The macro scale is simply a dimension reduction of the micro scale. So it's sort of very well understood. So let's take a particular example system, just so we have something a bit easier to grasp. And here we can define something that looks exactly like our model of causes and effects, right? Where we can say it's some sort of bipartite model, and it could have 8 states here. And for example, here we would say, okay, let's define this system. Let's say it's a Markov chain where 0, 0, 0 transitions 70% of the time to 1, 1, 1, and then 10% of the time to the other 3 states on the other side of the bipartite model. And every sort of state has this sort of relationship. They all have some 0.7 connection and some other sort of less likely connections as well. And down here is the transition probability matrix of this same system. You might be asking, what's special about this system? There's nothing special about this system. This is just going to be our example system for applying these measures. And we're just using it because it's so simple, because it's just, you have 2 sides of the model and the model just goes back and forth. But what that means is also that it has a very nice relevant macro scale of description, which is that, okay, forget exactly what state it's in. If it's 0, 0, 0 or 0, 0, 1, forget about it. I'm not going to care. All I'm going to care about is it on the left side or is it on the right side of the bipartite model? So it goes on and then off and then on and then off again. and you get this macro scale transition matrix, which is a coarse grain of the micro scale. And again, it perfectly, in philosophical terms, it's perfectly supervenient, right? We haven't added anything here. This is just a different level of description of the same system. And what's quite nice about this system is that it's very easy to scale the determinism and degeneracy, which is sort of the amount of noise within the model, right? So I won't get into exactly how we do that, but it's very easy to sort of play with the parameters of this system. Okay, and so here what we do is apply the measures of causation to the transitions within this system. So for example, the Galton measure of causation, you would see is generally positive during what we call the main transition. So that 0.7, this purple here, this would be like the main effect or the main transition, the main effect of this cause. So for the main transition, you see a positive value. For secondary transitions, you see a small negative value. You can look at the average transition. I won't go too into this there's sort of a background assumption here about how frequent are these transitions, and you have to sort of make a choice. Do you sort of intervene to do the transitions yourself? Do you allow the system in its dynamics to define it? We basically just do every possible background condition you can think of, right? So we can kind of remove the background conditions from this and just think about the model. So we can look at Suppes, Eels, Chang. These are all measures of causation. Lewis, another Lewis, and you can see they all also kind of behave the same. Actually, we include this bit flip measure, which I think was originally introduced, Sara, in one of your papers, and then the effective information as well, which is a measure that I've played around with a lot. But in general, it basically looks like these measures of causation sort of work. They sort of give us somewhat what we would expect in a system like this. And they have like very broad agreement, not all the time, but generally, about what's a strong cause and what's a weak cause. Okay, so what is causal emergence then? Causal emergence is just when your measure of causation returns a higher value at the macro scale than the micro scale for the same transition or for the same causal relationship. So it's basically like we're looking at causal relationships, both at this higher scale, this macro scale, and this micro scale. And we just want to know, is the macro scale greater? So here, so what we've done is that we've taken, for the exact same transitions, we've taken the measures of causation and subtracted the macro subtracted the micro from the macro. So the positive values mean that your macro is greater, and purple means that the micro scale is greater for this value. So for example, the sufficiency of state transitions at the macro scale is far higher, right? The necessity of state transitions at the macro scale is higher. These are, again, the same transition, just being described in two different ways, one of which is on the micro scale, one of which is on the macro scale. The determinism is higher at the macro scale. The degeneracy is lower, but that's actually a good thing because causation measures generally are the inverse. They track the inverse of degeneracy. So the less degeneracy you have, the stronger the causation is for most of these measures of causation. So this is, again, exactly what we would expect. If you look at the Galton, the Suppes, the Eels, the Chang, the Lewis, basically any measure we find instances where the macro scale transitions are rated as being stronger causes than the micro scale transitions. Okay, so you might be asking, wait a second, how is this even possible? So as I said, the boring answer is sort of that, listen, it's just noise reduction. So if we go back to here, you can just see that at the micro scale, there's uncertainty in the dynamics of the model, right? Like if you're at 0, 0, 0, you don't quite know where you're going to transition to. You might go to 1, 1, 1, but you might not. At the macro scale, if you're on the left side, you know you're going to the right side, right? So you have total certainty. So you've minimized the noise. And we can think of that as almost like a form of error correction. So like macro scales have a certain level of error correction that they're like adding to the system. But of course, the dynamics are no different at the micro scale or the macro scale. It's just that the causal relationships have a lot less error in them up at the macro scale. But let me give sort of the more complex, maybe slightly less boring answer, which is how, in terms of how this is possible, which is that, well, we can also think about noise reduction in another way, which is the conversion of information. So what I think is going on is that causally irrelevant information is being converted at macro scales into being something that's causally relevant. Okay, so how could we possibly like test this hypothesis about this is what's going on? Well, luckily, there's a really well-known measure of information, which is the mutual information, which basically is universally agreed upon. Everyone likes this measure. No one thinks it's like weird or unfair, and it behaves very, very well. The mutual information can actually be decomposed into it can be decomposed into three ways, but that basically looks a lot like a decomposition into causally relevant and causally irrelevant information. So specifically, again, I'm going to skip a lot of the details here because we only have 30 minutes, but for those familiar with the mutual information, this is called the partial information decomposition. And what it does is it gives you three types of values. It gives you the unique information, which is the unique information that each source has about its outputs, and then it has the unique information, the redundant information, which is information that's shared between sources. It has the synergistic information, which is sort of like the whole is greater than the sum of its parts aspect of information, which again is well studied mathematically. There's sort of nothing mysterious here. And we can break down the mutual information into synergistic, unique, and redundant. And I would argue that the synergistic and unique look a lot like sort of causally relevant information, and the redundant information looks sort of like causally irrelevant information. So we sort of invented our own little way of measuring how causally relevant the information is within a particular system by looking at the partial information decomposition, which breaks down a system into sets of interacting parts. And at the bottom of the decomposition, you would have like totally redundant information, and at the top of the decomposition, at this lattice, you would have fully synergistic information. And so here are two systems which are quite different. In the first case, so it has a low synergy bias. And in the second case, your bias towards synergy is very large. So you have a high synergy bias, right? So in the first system, the elements are sort of all doing their own thing, and they're all sort of copying one another. So they're totally redundant. In the second system, all the elements are jointly interacting to do something together, and the mutual information can capture this quite nicely. Okay, well, what we can do is we can do the same thing as we did with looking at direct measures of causation, except again here, the mutual information isn't really a measure of causation, but it can sort of be broken down into these parts quite nicely. So let's look at what happens when we do that. So a very common way of thinking about systems is to look at we can think about systems as logic gates, and logic gates can be made out of other logic gates. Right, so using the NAND logic function, you can make like any logic gate that you want. So this gives us a very nice model of macro scales versus micro scales, right? Where macro scale there's some like an XOR gate or something like that was made out of simpler NAND gates. And this should say macro scale actually on the right. So we look at the micro scale on the left and the macro scale, sorry for that, on the right. And you can see you can do this partial information decomposition to look at how synergy biased versus how redundant the information is at these different scales, right? And what you'll actually find is that in general, the macro scale is much more biased towards being synergistic and unique. The micro scale is biased towards being very redundant, generally, when it comes to information. Okay, but you could argue that that's interesting, but maybe it's just because at the macro scale, it's throwing out the redundant information. So of course, it's becoming more biased towards the unique or synergistic information, but it doesn't have more synergistic and unique information. That'd be crazy, right? Like, how could it have more synergistic and unique information at a macro scale? Well, it can, and we can show that directly, because what we can do is that we can create macro scales that are equivalent to microscales that have the exact same mutual information value. So I won't get into exactly how we do this, but you can think about it sort of like growing a system and then coarse graining over it as you grow it. And you can do it in such a way that, for example, if the mutual information of the microscale is 2 bits, you can make it so that it has some macro scale that's also 2 bits, right? So we have the exact same number of bits. So no bits have been added or have decreased, right, between the comparisons. And again, this is the same systems at 2 different levels of description. So these different levels of description, the mutual information is the same. Okay, and then when we do that, we can now still see changes in the synergy bias of the mutual information. So first we look at systems with some noise in them. And in systems with some noise in them, which we call Gaussian systems, you can see that as the macro scale gets more synergistic, the change in synergy bias increases. So in other words, you've had a positive shift towards being more synergistic at the macro scale, but your mutual information value has been locked. So where could that information have come from, right? It can't come from throwing out the redundant information. It has to come from converting the redundant information into synergistic or unique information. This isn't always true. And so this is something that should be really emphasized, right? Which is that in this sort of framework, there are plenty of systems in terms of their system architectures where you don't see any causal emergence, right? And so here, for example, the change in synergy bias, you can have instances, this entire region down here, which is labeled deterministic systems, you can have all sorts of systems where actually the microscale is more synergistic and unique than the macro scale, right? And has more mutual information. So, or actually, no, here it doesn't, here it's the same. But in general, causal emergence is something that depends totally on the dynamics of the system itself, on the system architecture. It's not like a universal. Like, so sometimes you have causal emergence, other times you have causal reduction, where actually the causal relationships are stronger once you fine grain the system. And I personally think that causal emergence, when you look and try to fit it into this notion of noise reduction and causal relationships into the philosophical literature, what you'll find is that it's not really strong, nor is it weak emergence, which are these terms that philosophers use to sort of try to pre-categorize concepts of emergence. And the danger with sort of pre-categorizing things is that you'll become sort of certain in your categorizations, and then the real thing might sort of be in a category space that you didn't expect. And in this case, we have direct measurements that showing that the macro scale is causally more relevant to producing the effect, right, by all these measures of causation. But supervenience hasn't been violated. That is, the macro scale system is just a dimension reduction or coarse grain of the microscale system. We haven't added anything. There's no extra magic. There's no extra laws up at the macro scale, anything like that. And so in this sense, it's sort of boring, right? And in that sense, I think that it's relatively successful in its boringness. If you want to know more, because my papers are always far superior than my talks, you can check out some of my recent work where a lot of this is being drawn from. One is a paper called Causal Emergence is Widespread Across Measures of Causation, which shows precisely what I showed in the beginning, which is that you can have a bunch of these measures of causation and they all show causal emergence. And then the second one is looking at this decomposition of the mutual information and showing that macro scales can become more synergistic and unique in terms of their information compared to micro scales, despite having the exact same bit number. So this is sort of like almost like a meta emergence paper, but I think it's quite interesting. And thank you everyone so much for paying attention and for tuning in tonight. And thank you.
Thank you, Erik. Let me seize control as moderator, and I want to bring in Sara Walker in a moment. I just got a couple of comments I want to make. One concerns, it's a comment about eels. I once went ice skating with his daughter, and she said they pronounce their name Els. So that's, so you can store that little fact.
That is important. Thank you so much. That's great.
And the other is that I, over the years, probably like you, have got into arguments with people about that you might know everything about the superstring Lagrangian or whatever you think the world is made of, but you can't figure out how I'm going to vote in the next election because I'm an open system. And then the reply is usually, but if I knew everything that was going on in the entire universe, then I could predict exactly what you're going to do. And so in the end, the microscopic variables are going to be adequate in principle. But the universe is an open system. And at that point, the discussion normally fades away. So I'm not asking you a question. I'm just pointing out that that's something we might want to get into. So I'd like to hand over to Sara, who thinks a lot about these sorts of topics. So Sara is, of course, co-host of Ask a Physicist, that will be familiar to our audience. She's Deputy Director of the Beyond Center. And Sara, would you like to pick up the discussion?
Yes, and I'll also invite our audience to start entering any questions they might have into the Q&A. And we're going to have lots of time to answer questions for everybody in the audience as well. Erik, thanks for coming. That was really fun. I think my role today is supposed to play contrarian and sort of like on the other side of the debate, but obviously I agree with you that emergence is a real thing and necessary to explain and should be explained with mathematical principles. So I actually want to ask a sort of different question than how I might disagree with the boring notion of emergence. I like that you said it was boring, although I don't actually. It was quite funny because sorry, I'm just going to make this side comment because I was laughing when you were saying most explanations when we have them are quite boring, and I was like, that's not true. We have the laws of motion and like Newton's law of gravity and Einstein's theory and all these things, and then I was like, probably most people think they're boring. But I don't think they're boring. I think they're very elegant. But they do have a certain explanatory depth to them. And I know you get this question a lot, but there's always this question of like, if you explain something you haven't explained before, and you take a philosophical concept and you turn it into a scientific one, presumably there's more you can do with it once it's in the scientific space because you have a deeper understanding and you have some mathematical formalization of it. So I guess my question is, now that you're thinking that this is a way of formalizing causal emergence, what next? What do you do with the boring answer? And what your ideas are on that. And I can ask in a specific case because, in my field, people will talk often about the quote unquote emergence of life. So if you were going to apply your formal definitions, what would the emergence of life actually be? Or would that not qualify in sort of the set of things?
Yeah, great question, Sara. So sometimes people use emergence sometimes in two ways, right? And one way is sort of the emergence of complexity from simplicity, like a cellular automaton might might sort of show emergence in that it starts very simple and then develops something sort of complex patterns or something like that from simple rules. But I do think that life would qualify like under this definition of emergence, and I also want to, and we actually have some evidence for that now, but I want to sort of address this first point regarding the boringness. So I think that the important and the what does it matter, right? So one of the things I've been a big proponent of and a big critic of the philosophical literature is that most of the time the notions of emergence that are put forward simply have no bearing on anything. So here, for something to be scientific, it must be somehow useful. It has to be somehow useful to someone. And you can think about this as like, imagine that I have an emergence detector and I go around and I detect emergence in different systems, right? And then the question is, what information does that give me that's at all relevant, right? And if emergence was totally this sort of metaphysical concept, then it really wouldn't be giving me anything relevant. And in fact, I've never seen anyone in the philosophical literature really have any sort of notion of emergence that does give something relevant. So in causal emergence, I think that there's a couple very clear scientific questions that you can answer perhaps only with a good theory of emergence. And let me give one from my sort of home field, which is neuroscience. And in neuroscience, there's been a raging debate for about 100 years about what is the functional unit of account or spatial temporal unit of the cortex. So if you're a proponent of the neuron doctrine, you could say, listen, what really matters is the state of all the individual neurons. The individual neurons are the ones really doing sort of the computational work of and cognitive work of the brain. But there are some people who say, actually, no, it's actually a lower scale than that. It's actually the molecular machinery of the synapse, which is really sort of doing all the important work. And that's really how we should think about the brain and describe the brain. And there are other people who say, no, it should be mini columns of 80 to 200 neurons that sort of span the cortical layers. And other people say, no, it should be cortical columns in general. Those are really sort of the fundamental unit of account. And when you think about something like a brain imaging device, you ask, well, at what scale should you be looking and correlating, behavior to within the neurosciences? What's the spatial temporal scale? And my answer to that would be, it's the causally emergent one. If you could sort of look at all the causal relationships in the brain, and that's very difficult to do, but sort of hypothetically, and you were able to calculate causal emergence, you would find that causal emergence is you'll find the scale at which causal emergence is occurring, which, let's say, for argument's sake, it's the mini column scale. That's sort of the actually causally relevant scale in terms of the relationships of parts of the brain to one another or its output to behavior. And it would sort of give you the scale of interest that you could, for example, build a neuroimaging device on. Another example from within neuroscience, which is basically the same question, is if you were going to build a huge model of the brain, like they wanted to do at the Human Brain Project or at the Blue Brain Project, right? That was planned to build like $1 billion model of the brain. At what level of description would you sort of start building your model around? What would be the relevant level of description? And even within somebody like for Richard Dawkins, right? He's one of the big sort of debates that Dawkins has participated in his kind of in his time, and one of the things he's very known for is this debate over scales of selection in evolutionary theory, right? So is there any group level selection that's really going on, or can it just totally be reduced down to just genetic selection of individuals? And Dawkins says, yes, it's just gene's eye view, right? But Wilson says, no, it's this group level selection going on. And so it's like, how do you resolve those debates? Well, my guess would be that actually a really good way to do it would be to have some relevant notion of emergence and look at things like at what scale, is the most selection going on, and at what scale is sort of more causally related to the actual phenotype, of the organism or something like that. So I do think that there are real useful questions that we can answer using these sort of things. And they're questions that pop up in the sciences all the time.
So if I was going to paraphrase that last idea, is it like if I went into a system and I didn't know the relevant scale for building a mathematical model or theory to describe that system, I could apply causal emergence to tell me what scale I should actually be thinking about, even trying to develop mathematical formalization for describing the effective dynamics?
Exactly. And we're so used to certain systems that like oftentimes we design systems like computers. So we know computers sort of operate at, the level of machine code or some other higher scale. And you could still say there's some debate, right? Because you could legitimately describe it at machine code versus the higher scale. But in many systems, particularly biological systems, we kind of come to them as if they're alien artifacts and we don't know what scale is of importance. And there's where I think a scientific conception of emergence can give us real definite answers and useful things for scientists.
Yeah. So another sort of related question I have to this idea of like identifying relevant scales to model, which I think I've asked you in the past a few different ways, but every time I'm still curious your perception on it. And I don't think we've had a long enough conversation to really tease into it, but it seems to me that a lot of these things are somehow observer dependent. Like we're building the models, we're talking about the relevant scales for describing them. So I always think of causal emergence as being a relationship between an observer and an observed system. But yet at the same time, when we talk about things being causally emergent, it's supposed to be an intrinsic feature of that system. So I wonder how you think about that from the measures and what you've proposed for us today, and also from your own perspective on what you know of lines and their interaction with reality.
Yeah, so it's a great question. I would say it's sort of dependent on what you feed into the model. So so if for example, let's say that I'm only interested in certain outputs, like I'm only interested in how, cells get cancer or something like that at some very particular sort of output, right? Now, the causal model that I'm going to have when I go to ask that question is not going to be a complete causal model of everything that's going on in the cell. I mean, at least generally, right? It's going to be sort of some sort of limited causal model, right? And causal emergence is calculated off of some causal model. So in this sense, you could have, a causal model that's sort of incomplete. You can calculate causal emergence, and you might say, well, listen, it's sort of there, but it's sort of observer dependent. Like it's just because it's only present because we, have the model set up like this with the certain background, conditions that we choose. But I think that there's also another way to think about it, which is as sort of close to complete in its totality description of the causal relationships of the system. So for example, within the brain, this might be like the causal relationships between the set of causal relationships between all the neurons of the brain, right? And, somewhere in there, there's some, very particular questions, but there's sort of this much broader description, just like a full model. And then in the full model, you'll be able to find, causal emergence at some, particular scale. I mean, at least generally, if there's some noise in there and so on. And at that point, I would say, that's closing in on what we would want to call like an objective intrinsic scale of function, right? Like this is where the work is actually sort of happening. This is a spatial temporal scale at which the work is actually happening. And yes, you could always ask other questions like, what does this atom relate to this atom in the brain, right? Like you can always ask that question. But if you look at the full sort of set of causal relationships within the thing itself, that's like totally washed out and it doesn't matter causally. And all that really matters is sort of the macro state of these neurons or mini columns or what have you. So to answer the question, I would say, I think that once you start really talking about like full causal models, and really like having totally complete levels of totally complete descriptions of systems, which is very, very rare, of course, then you're starting to talk more about something that looks like an ontological fact or like an objective fact about the system, that this is the scale of function, this is the scale of importance in the system, and importance taken broadly.
Right. So can I use my opportunity? I just want to have one more question. I know we have questions lined up. Sorry. Which is just on the point of the let's say when you show to a physicist, and since Zach's a physicist, I felt compelled to ask this question, a whole bunch of equations that describe the same thing but are slightly different. Our mind goes toward, oh, there should be a unified theory of this. So in your mind, is there a unified theory that like unifies all of the sort of things that you're talking about and you have sort of one mathematical form you could settle on? Or do you think it's always going to be, pick and choose your favorite equation for your favorite application?
Yeah, that's a great question. The one way that I think about it is that there's a sense in which it might be asking too much of causal emergence to solve causation as well. So like it effectively, it's like, listen, this is a fact about causal relationships that we observe across these measures. Presumably, if someone comes up with some new measure that was somehow some sort of unification of them, because it's shown up in all the measures, it presumably would show up in that sort of unified measure. I would like to see a more unified measure. I think some of these measures are not that good, and I wouldn't like really use them or prefer them. But I think my point is that this phenomenon is not measure specific. If it was deeply measure specific, and this was what, by the way, early the sort of the early causal emergence papers that I worked on with Giulio Tononi and Larissa Albantakis back in like now almost 10 years ago, that those papers, what people, we use this one measure, which is called effective information. And what people seized on was like, is this the perfect measure of causation? And then they were sort of like, well, if there's a problem with the measure, maybe causal emergence is sort of this weird artifact of this one measure, right? And I think that that's like a legitimate criticism. I don't think it's correct, but it's like a legitimate criticism in that if it was just completely one measure dependent, then it would be a problem. But we see it across all sorts of things. So it seems pretty universal, and therefore sort of much more objective in that sense.
Okay, now we've got a couple of questions that have come in. Before we take them, I've been struggling to distill the elevated speech from your presentation. You had a lot of arrows. Am I right in thinking that a general point here is that somehow coarse-grained macroscopic variables can sometimes have more causal clout than their components? I mean, I'm not using a technical term, the causal clout, but I'm trying to get to the heart of this. Is that sort of roughly speaking right? Because
that's exactly right, exactly right. And the notion of clout, of course, what clout is depends a bit on the measure. Like for some people, clout is sort of, the strength of the dependency or the counterfactual dependency, or there's sort of a family of things under the notion of clout, but all of them show it. So I think it's sort of an objective fact that macro variables can have more clout than micro variables, even though they're the same, right? They're just different levels of description.
So now let me bring in a question we've received from Barbara Temple, part of which I think you've addressed, because she's had, there are actually three questions here. Is consciousness strongly or weakly emergent? And you said you didn't like those categories. So do you want to say anything about that, or should we just move on to the next question?
It's a really good question, and I think it's really interesting. If I was going to list any property in the universe that might actually be strongly emergent and violate supervenience, perhaps consciousness is the one. But despite having done research into consciousness and having a background in neuroscience, I try to purposefully not talk about consciousness when it comes to emergence. What I would like is a theory of emergence. What I would like is a theory of emergence that's really, really so simple, and again, sort of boring, all just based on like Markov chains and no reference to anything that might be relatively, controversial or difficult, like consciousness. I think consciousness is one of the most difficult and open questions in all of science. So I sort of purposely avoid it, but I do think it's very interesting.
Well, if you think that's bad, then her next question is about free will. Is that an emergent property? So I imagine that your answer would be similar. You would rather not talk about it.
Well, so actually, funnily enough, I think I'm closing into the point where I'm more comfortable talking a bit about free will, because I think that at least at the very basics, the theory is sort of sketched out, and in my opinion, sort of difficult to argue against at this point. And so within free will, I do actually think that causal emergence is relevant. I don't think it by itself proves free will. As I said, very simple systems show causal emergence, right? And unless you want to say that macro states somehow have free will just because they have more causal clout than their underlying microstates. But I will say that if you look at arguments against free will, one of the main arguments goes something like, well, you didn't cause your actions, your atoms did. Like your brain is in some quark cloud state, and that quark cloud is the actual cause. And we know that because of this sort of reductionist assumption. What causal emergence says is that that's not necessarily true. In fact, it's probably very unlikely. And actually, the cause was some relevant macro scale variable. What was the cause of the more clout was some macro scale variable, which may be like some psychological fact or something like that. But then consciousness and so on has to sort of enter the picture, and it gets very complicated. But I do think that it refutes that common argument against free will, although that's not the only argument against free will.
Okay, just very briefly, Barbara points out a comment that's often made about emergence, that it's a sort of mysterianism, and she wonders whether somewhere between reductionism and mysterianism there isn't a good explanation of in this case emergence. And I think you've been at pains to say yes, we can have a boring explanation. She describes it as a decent explanation, but decent and boring could be the same. So I think probably you've taken care of her third question. But Barbara, if that isn't the case, then put through something on the Q&A channel. We have a question from Brian Daniels. Do you view your causal emergence measure as essentially epistemological or ontological? So for our viewers, listeners who don't know the difference between that, I think epistemology is what we know, ontology is what is, very briefly. So is the fact that causality is easier to describe at larger scales only relevant from our limited viewpoint? But I guess that will make it epistemological. Do you have a quick answer to that?
Yeah, so this is a good question, and let me separate them and answer the second one first. So regarding a limited viewpoint, in the systems that we're working with, one of the main things we do is make sure that they're small enough that we model the full system. So there's no sort of like missing microscale causes within the systems that we're looking at. So certainly within our model systems, they're sort of, it's really not a problem where we just don't have a limited viewpoint. But the broader question is, I think like an interesting one. You know, a big aspect of this is whether or not causation is epistemological or ontological. And I don't, you know, I try to sort of be as modular as possible, which is basically that, like, listen, causal emergence is based in causation. If you have some radical, I think relatively radical philosophical positions about causation, like maybe causation is not really ontological, nothing is really caused in nature, it's just this sort of epistemological notion, then in that case, causal emergence would also be just a purely epistemological notion, because it's just some fact about noise reduction in causal relationships at higher scales. So I think that the answer is that it sort of depends on a lot of things, but I don't think that it's obviously epistemological. I think it can be something close to what we would call an ontological fact about the system, that it does have this higher scale that has more causal clout.
So we've got another question. This will be our last, I think, from Paul O'Brien, and I'm struggling to summarize this, that any measure of causation or any observation would involve an increase in the entropy of the universe. I think we're all used to that. That nothing you said today, Erik, would suggest that there's anything different about the second order thermodynamics. So the question at the end is, if every thought increases the measured entropy of the universe, does it increase the volume of the universe? I don't quite myself see the connection there. We can measure the volume of the universe, not with very great accuracy, but we can measure its increase every day. It can't be reversed. I don't think we can reverse the expansion of the universe. So it may one day do so on its own. So I'm not sure how to put that question to you, or whether you can read it, or whether you have any comments on that. But it ends with, do you agree?
Yeah, I can't quite, as I said, I'm not a physicist, and so I try to avoid actually talking about things like thermal degrees of freedom or so on, and I do so for the reason that I actually think is pretty defensible, which is that science is concerned with causal models well beyond the physical. So, like, for example, biologists might have a Boolean network or a gene regulatory network, right? Neuroscientists might have brain states or so on. And all these things aren't really physical concepts. They're sort of just models of systems, and models being like an abstract set of abstract relationships between variables, right? So I think any notion of emergence has to work across that sort of field, that wide swath. I'm kind of leery of notions of emergence that are based entirely within physics. That also maybe just because, again, I'm not a physicist. So unfortunately, I can't directly address Paul O'Brien's point. So that's why I can't directly address it, at least.
Well, thank you very much. We do actually have a last minute quick question by Yambo. You mentioned a boring explanation, noise reduction. In many cases, physicists often develop macrostates over microstates that are not considered as noise. Can causal emergence theory address this thing?
Yeah, so it's a subtle distinction between when I say noise, right? What I mean is noise within the causal relationships, and you're actually not grouping in your macro state across a bunch of noise. You're grouping to minimize the noise between the sets of microstates. So maybe a better term that a physicist might recognize is something like an equivalence class, right? So like if you have all sorts of underlying microstates and they all do the same thing or lead to the same result, then that would be a very good grouping into a macro state. Like all the measures would generally show causal emergence in that instance. So I don't know if causal emergence perfectly lines up with the sort of the standard macro states of physics. I think that that's a really interesting and in my mind, like open question. But I think that there's a good reason to not know it, right? Which is that, first of all, just what precisely is causation within physics? And I think that you can kind of get different answers to that. And that's sort of a big open question about how do you translate this notion of causation out from just these abstract models into the physical world. But again, I think that that's just a bit beyond the purview of causal emergence, right? Like if it turns out you can't do that, for instance, then yes, causal emergence goes down in flames, but so does like all notions of causation, right? So it's sort of so I'm very interested in sort of applying this to physics, but I'm very like weary of it, and so I generally don't. But so I don't quite know exactly the answer to the question.
Okay, we're going to have to wrap it up because if you haven't had dinner yet, it's getting awfully late where you are, and it's even getting to dinner time here in Arizona. So I'd like to thank you, Erik, for giving us a lot to think about, a lot of arrows there. I will digest, and the relevance to your the references to your papers are really very useful. And that brings us to the end of this semester's Ask a Physicist. Stay with us because there'll be further events coming up in the fall. Just follow the website. So it just remains for me to thank you once again, Erik and Sara, for your contributions, and for Jessica for driving the whole thing without any hitches. And I'll say good night to you all and sign off.
Thank you so much, everyone.
Bye, everyone.